So let's perform the visualization step by step. Once again, we make a call to this function. Once again, I have the list as before, but this time the 0th item is the string 0. So when I come into the function, this is not the base case, this is a non-empty list, and now I ask this question: is data 0 remainder 2 truthy or falsy? Well, data 0 is not a float anymore, it's a string. And what is the meaning of taking a string remainder and integer 2? Well, when we click on next, we get an error message. We get a type error that tells us that this is an illegal operation. So you see, this code isn't particularly good. It doesn't do what our friend said it does, because in this case, in this list, it does have an odd integer, but this function is unable to find it. But let's see if we can improve this code. So I'm going to give you a better solution, one that will be able to work on heterogeneous lists like this one. Our basic idea is going to be to simply examine each item in this data in sequence. We will examine each item iteratively. This is very similar to the way a human would. I give you a list of values, well, you would look at them one at a time in sequence. Now, if the item we're looking at is an odd integer, we would return true. On the other hand, if the item is not an odd integer, we would just continue to the next item. So when we looked at this item, we would say, that's not an odd integer, move on to the next. This is not an odd integer, move on to the next. This is an odd integer, we would return true. Now, what happens if we scan through each of these items and we never find an odd integer? For example, what if the list did not contain this last item? It only had these two items. Well, then after we have examined every item iteratively, there will at some point be no more items to examine. Well, in that case, we will return false. So we will say we weren't able to find an odd integer. So hopefully this strategy, at least when expressed in words, is very intuitive. If I asked you to search for an odd integer in a given list, this is probably how you would go about it. Unfortunately, the equivalent in Python looks very similar. Here is that code. So we have a function, we haven't called it mystery anymore, we've called it hasOdd, which is a much more meaningful name. We probably should have given a doc string here, but I haven't done that. You can think about adding that. Anyway, given a list which could be heterogeneous, this is going to return a boolean. It's going to return true if that list has an odd number in it. How does it work? Well, it examines each item in data. This Python syntax, where we use the special word for and the special word in, achieves this. It examines each item in the given sequence, in this case this list data. It examines each item, and we call this iteration. Now, remember, we were supposed to check if the item was an odd integer. And so how do we check for oddness? Well, we calculate the remainder mod 2 and we check to see if that is a non-zero value. As we have seen, we can just simply calculate the remainder mod 2, and that will, if that is a non-zero value, that would mean it's odd. And how do we check if it's an integer? Well, this condition will work. Is the type of the item an int? But not quite, because as we have seen, if the input we give is a string, then calculating this is going to fail. It's going to produce a type error. So how do we check if the item is an odd integer? It's very simple. We first check this condition. So we write the code like this. Remember, the difference between the previous code and this code is important. We are taking the AND of two conditions, but remember, AND works with this short circuit logic, which means that if the type was not an integer, such as for example for this string, this condition would be false, and false and anything is false. So the short circuit logic does not calculate the remainder of the string divided by 2. So we avoid creating a type error if we write the code like this, whereas if we wrote the code like this, we would get a type error. So you see, this is an example of how we as programmers can make use of short-circuited evaluation both with ANDs and similarly with ORs to write code that is simple to read and also correct. Now, crucially, look at the placement of this statement, return false. Remember, we want to return false after examining all the items in the list. So we place this statement outside the for loop. The for loop ends with a colon, so no surprises. Every statement inside the body of the loop, the set of statements that have to be repeated each time, are indented at least one level. This return statement is indented 2 levels because, of course, it's inside an if condition. But this statement on line 5 is not inside this body of the for loop. It is outside. So this statement happens only after the loop finishes, only after we find no odd integer in the list. So this version of the code is better than the recursive version for several reasons. Firstly, it's more robust because, as we have just seen, it does not fail on inputs like this. We have fixed that problem by writing this if condition carefully. Secondly, and perhaps more importantly, this code is more efficient in what we call the worst case. Now, I'm going to introduce some technical terms here. Unfortunately, we don't have enough time in this course to examine these ideas in full detail, but it's important for you to know that we as programmers want our code to be efficient. We want it to run quickly and we don't want it to consume too much memory. And I will introduce these ideas of code that runs in linear time using a linear amount of memory versus code that runs in quadratic time and uses a quadratic amount of memory using this simple example and the recursive code that we saw earlier. So let me give you a high-level intuition of what this means. Imagine you had a list of size not 3 but some large number n. Now, how does this code work? Well, it examines each item in that list. Now, if we get lucky, we will find that that item is an odd integer and immediately we will exit the function. But in the worst case, we would have to examine each of these items, and perhaps only the very last item in this list is an odd integer. Or maybe even that last item is not an odd integer. And so we examine every item in the list, and then after examining everything, we come out and have to return false. So the worst case really would be when none of the items in this list are odd integers. Of course, we don't know that. We have to examine everyone because perhaps one of them is an odd integer. So in the worst case, as this number gets bigger and bigger, we have to spend more and more time. But this growth is linear. The length grows more, the time grows more, but it's a straight line. On the other hand, think about what happens in the old recursive code. In the recursive code, we don't examine every item right away. We just examine the 0th item. And remember, if that is not an odd integer, we make a recursive call on the slice considering everything starting at index 1 all the way up to the end. So that slice requires us fresh memory. We have to take the original list of size n and now make a copy of the last n-1 items. If the 0th item there is not what we want, then we have to make a slice of length n-2. This is going to cost us both memory and time. Making this fresh slice requires us to copy information from the original list. So this is going to cost us both time and memory. And roughly speaking, if you look at this kind of a pattern, you can consider it like a triangle which has width n and also height n. So roughly speaking, its area is n square over 2. Remember, half base times height for a right-angled triangle. So this is the sense in which the recursive algorithm takes quadratic time, because it takes time that is n square divided by 2, whereas this code takes time that is proportional to n. Now, these ideas can be made more precise in a course where you study algorithms and algorithmic complexity, but in this course we will keep our discussion to this intuitive understanding.